All right, now we're going to talk about something that is pretty easy to create confusion. We introduced it in the end of the last lecture, the dimension of the classical groups. Now, I pointed out that the notion of dimension is always present whenever we're dealing with a vector space, right? We always have a vector space of a certain dimensionality over a field, and in our vector spaces all now are inner product spaces. We all have some inner product, which from now on we're really going to be talking about inner products that are either sesquilinear, Hermitian, or bilinear, anti-symmetric, right? Those are the two sort of main things. So this is a dimensionality n. And then we know that depending on what metric you have, and depending on whether or not you want to be volume preserving, there's some group out there that is metric preserving, volume preserving, or both or either, that is an isometry group. An isometry group. Well, if it's an isometry group, it's almost always the isometry group of the metric, right? So this would be more of a metric preserving group. So let's just say it's one of the metric preserving groups, and it may or may not be volume preserving. But this isometry group contains matrices, and I'll call the matrix A, and it would be I, J, right? This is typical way of writing a matrix in order to preserve, say it's a basis transformation on J, so it would kind of look like that. We would get our up-down notation, and we're doing sort of the basis vectors are interpreted as columns. I hate to go all the way back to that stuff, but we're going to talk about Aij as a matrix element. And we know that if this is a basis transformation of an n-dimensional vector space, this is going to be an n by n dimensional matrix, right? And therefore, it will have n squared elements, right? N square numbers, each of which is drawn from the underlying field F, right? So in principle, there are n squared elements, and you could say, well, let's forget that it's an isometry group. Let me back off of this. Let's just say that it's the group of all possible matrix transformations. So this is GLNF. Now, I've kind of putting these brackets here makes it silly. This is understood to be the set. So making it the set of something that's understood to be the set is kind of absurd. So I'm going to get rid of those. Okay. So, but A is a member of that general linear group, and there's n squared values, independent values you can pick to be a member of that group. So you quickly ask yourself, well, okay, I can pick n squared independent numbers out of this general linear group. Well, how much independence really is there? Well, if it's the real numbers, right, the real numbers, each element, right, each Aij is an element of the real numbers. Well, you can pick one real number for each matrix element. So that's good. So that implies you have n squared choices. But what if F is the complex numbers? What if Aij is from the complex numbers, meaning our choice of F is the complex numbers? Well, the complex numbers themselves have a dimensionality of 2, and if I can pick n squared of them, now I have 2 n squared independent choices I can make for an invertible matrix that is that could represent a type of basis transformation of this vector space. So I have 2n squared. And if I'm dealing with the quaternions, right, if Aij is an element of the quaternions, that's 4, and now I got 4n squared, right? And so now this number 1, 2, and 4, the way Gilmore uses the language is he says, when the complex numbers and the quaternions are considered as vector spaces over the real field, right? That's the language he uses. So what he's basically saying is that consider the complex number as a vector space over the real field. And that would mean that the complex numbers, C, are a two-dimensional vector space whose basis is 1 and I, right? That's the basis. and the field it's over is the real numbers. And sure, any complex number A can be written as any complex number A, well, let me say any complex number, it's a little more conventional to use Z, is some real number A times the basis vector 1 plus the real number B times the basis vector I. So when you think of the complex numbers as a two-dimensional the two-dimensional vector space over the real numbers, meaning the scalars are real numbers, its dimensionality is 2. Likewise, for the quaternions, you do that, your dimensionality is 4. But this is kind of a weird thing, because now we're talking about, think of the reason this can be confusing, right, is ultimately we have a vector space, which is sort of the carrier space, if you will, of these matrices that are defined as all possible invertible basis transformations. Well, basis transformations is by nature invertible, but all possible basis transformations of an n-dimensional vector space with a metric, and that n-dimensional vector space has dimensionality n, and then we're talking about the dimensionality of this matrix, which would normally be considered n-dimensional in terms of matrices, but now we're kind of interested in how much actual dimensionality do you have in here, depending on what group we're talking about. And then on top of that, we realize, well, wait a minute, these matrix elements could be drawn from this underlying field, and that field has a certain dimensionality to it, meaning it's either 1, 2, or 4. And that's when you think about this field, which is the scalar field of this vector space. Now you're thinking about that field as a vector space in its own right in order to count its dimensionality. So this is why you kind of got to concentrate on this, right? It's not that difficult, and we never really return to this, but understanding that the quaternions, and we're trying to figure out how many numbers you need to define this metric, or this metric matrix, or not this metric, I'm sorry, this member of the whatever classical group we're dealing with. And we're not talking about necessarily individual matrix elements, because that's always going to be n squared. But each individual matrix element also has a dimensionality to it, depending on what field it is, right? So anyway, Gilmore mentions that, but he doesn't dwell on it, and I think it's worth dwelling on it. But what he does say is the dimensionality of these fields, F, is either 1, 2, or 4, depending on whether you're the reals, the complex, or the quaternions. And therefore, for the general linear group, you're always going to have F times n squared independent numerical choices to make to create that matrix, or a given element of that group. All right, so we can think now of the general linear group and F. We'll just focus on, just to keep things clean, F being either real or complex for right now. Quaternions are always a little exceptional. They do fit very nicely into the scheme overall, but it's almost like it takes too much time to talk about them, and we don't definitely need to dig in right away. So we'll usually talk about real and complex, and then we'll say, oh, and then for the quaternions, we think of them this way. Because very frequently we take the quaternions and we convert them into complex numbers anyway, using that, or 2x2 complex matrices anyway, right? Remember how we learned that a quaternion can be considered like, let's see, it was alpha bar, beta minus beta bar, right? So quaternions can always be turned into complex numbers, and likewise, each complex number can be determined into a real 2x2 matrix. So you can turn a quaternion into a real 4x4 matrix. Remember we did that earlier in these lectures. So ultimately, you can you play with that, and you can convert all the quaternions into quaternionic groups into real or complex groups. But right now what we've shown is that the general linear group in n dimensions over the reals or the complex will have f n squared independent little choices in the matrix, where f is either 1 or 2, or if you're going to include quaternions, 4. All right, so now if you take out an element, say A, of the general linear group, and you examine the determinant of the matrix A, I, J. So the two bars there sort of indicate the matrix 2ij. And you insist that the modulus of that thing equals 1. The modulus equals 1. Well, then that is a restriction that, of course, means A is thereby an element of the special linear group of n dimensions over the field F. Right? That was the definition of the volume preserving group. So if you do that, then for real fields, this determinant equation will force at least one element to depend on all the others. So you lose one degree of freedom. If it's complex, if you're dealing with a complex field, then in order to have this happen, you have to make it equal 1 plus 0 I, right? Which means you need to force everything equal 1, and you have two constraints, right? So you lose 2 degrees of freedom. So it really depends whether you're dealing with a real or complex field, how many degrees of freedom you lose in order to be in the volume preserving groups. So let me write that down. All right, so here I've now written that out. I've just basically said, all right, we've got our general linear group with Fn squared independent choices to define any given basis transformation in the general linear group. I'm now going to restrict Fn squared when I consider the real case, F is 1, and volume preserving means I lose 1 degree of freedom, so I have n squared minus 1 degrees of freedom for the special linear group over the reals. The special linear group over the complex numbers has inherently, as a subspace, as a member of GL, it would, as a member of the general linear group over the complex numbers, it would normally have 2n squared degrees of freedom, but it loses 2 degrees of freedom because you now have to force the determinant to equal 1. All right, but now we have restrictions associated with, that was the volume preserving groups. We have restrictions associated with the metric preserving groups. And those restrictions look like this. The metric transforms given if A is a member of the general linear group. This is how it transforms for the sesquilinear case. And the metric is presumed to be Hermitian symmetric for the sesquilinear Hermitian symmetric, and it is presumed to be in the bilinear, or in the antisymmetric case, it's Gij equals minus Gji, and there's no bar. This could actually, so you could also say it this way: Gij equals plus minus Gji, and that covers the bilinear symmetric and the bilinear antisymmetric, right? You could, I mean, the point is the constraints all look like this. You have to sort of choose which metric you're dealing with, which is equivalent to saying, where am I, hold on. Well, it's equivalent to saying, where am I in that diagram of, symmetric, antisymmetric, sesquilinear, bilinear. Remember that chart we made last time. That this is sort of characterizing that chart. The point is that you get additional constraints from this. So how do those constraints look? Well, the AB matrix element has a constraint equation. So that's one constraint for every matrix element for every GAB that exists. So that's kind of important, right? So that's a constraint for every AB. But these symmetry properties connect AB with BA. So the way we say it is, let's just consider the circumstance where A is greater than B, because when A is less than B, we just use the symmetry property to flip them around, right? So we get one constraint for every circumstance where A is greater than B.
All right, so if this is our equation of that constraints thing, and we're trying to count them up, we've decided we want I greater than J. So say we're dealing with n dimensions. right? N dimensions. So we'd be, the indices would be 1, 2, 3, dot, 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 up to n. Well, if you look at this, then for n, there's n minus 1 ways where the nth index, as if I was equal to n, there's n minus 1 possible ways of I being greater than j. If I is n minus 1, then there is n minus 2 possible ways for I to be greater than j. So this logic isn't too hard to see. What we're interested in doing is adding up I minus 1 from, well, the way I did it was from n to 1, but we'll just do it from 1 to n, like that, right? So we're looking for the formula for 1 to n of the sum of n minus 1. But it's probably, in my head, I can imagine doing this from 1 to n minus 1. Make the substitution I equals I minus 1, right? And so you're looking for the sum from 1 to n minus 1 of I. So this formula is not too hard to figure out, right? This is like that remember Gauss's sort of legendary thing where he was told to add the numbers between 1 and like, I don't know, was it 100? Maybe it was up to 99. And he realized, 1 plus 99 is 100, 2 plus 98 is 100. So it's going to be, 100 times, I guess there would be times 100 over 2 times 50, right? And so that formula, when you work that whole thing out, then you learn that the formula of the sum from 1 to n of I is n times n plus 1 over 2. And using that technique, we just substitute n minus 1 here, and we end up with n minus 1 times n over 2. And that's our answer. So this expression here gives us n times n minus 1 over 2 constraints. And it doesn't matter what Gij is. This is going to be true for any of the metrics that we're concerned about, the bilinear, the sesquilinear, or the symplectic. The only difference, well, the symplectic quaternionic metric, right? The symplectic metric, this, no, this is true for all of them. This is true for all of them. The only difference is that each constraint is multiplied by 1 for the real case, by 2 for the complex case, and by 4 for the quaternionic case, because each of those inherently has 1, 2, and 4 degrees of freedom when considered as a real vector space or a vector space over the real field. Now we have a look at constraints related to the diagonal elements of the metric. And this is all part of the metric preserving constraints. This is the second part of those constraints associated with metric preservation. And here I've written it in the bilinear form. And let's take a quick look on how this might affect things. The first thing you might do if you see this, well, first of all, there's n of these constraints, right? So there's going to be n constraint equations like this. And n separate constraint equations. However, if we take a look at the symplectic case, the case where Gij equals minus Gji, right? The sequence of steps to show that there's these diagonal expressions do not provide any constraint at all, meaning they don't constrain the symplectic case at all. It's pretty simple. The first thing we'll do is we'll rewrite this. We'll commute these things, A, J, A, I, G, I, J. So right away when you see I'm commuting them, I'm talking about real or complex. I've just omitted the quaternionic case. Then once I've done the commutation, I've changed the I and the J, right? I'm going to swap the I's and the J's because they're dummy variables, right? I can do that, right? So this becomes Ji. And then I use the symmetry property to replace this. And I end up with minus. And so this here converts quickly to that. And this has to equal this, right? Because this here is what we started with, just commuting these two here, commuting those two here. So, but this piece here is equal to this piece in the world where things commute, which we've already presumed, and of course this equals this. So this and this are the same except for this minus sign, and the only way something can equal its opposite is if it's identically zero. So the diagonal constraints for the real or complex case of the symplectic metric are identically satisfied, and therefore they don't contribute a constraint at all. But that's not true for the other cases. For the orthogonal case, this constraint is the real deal, and you end up with n of them. And for the unitary case, this constraint is the real deal. But remember, the diagonal elements of a unitary metric are real, right? Because you're dealing with, you have GAA equals U, well, not U, use a bad choice. The eighth basis vector and the eighth basis vector, where I'm saying eighth, not eighth. But this has to be real because it's a Hermitian in the unitary, or it's the sesquilinear Hermitian metric. So this is real. So each of these equations is a real equation, and therefore in the unitary case, each equation, because it's forced to be real, is only one effective constraint. In the orthogonal case, you now are dealing with you have n, but you have one. Each constraint equation eliminates 1 degree of freedom for the reals, eliminates 2 degrees of freedom for the complex number, and it eliminates 3 degrees of freedom for the quaternions. Now, I would have expected this number to be a 4. Right, not a 3, right? Because the quaternions are 4-dimensional with respect to when understood as a vector space over the real field, right? But the actual answer is 3. And this is a photograph right out of Gilmore, where he finally sort of adds up all of the he calculates the degrees of freedom for this orthogonal matrix in n dimensions for f. But because he has f and he breaks out the quaternions here, that f is only applying to the real and the complex numbers. So this is the total number of degrees of freedom you would naively expect in an n by n matrix of either real or complex numbers. It's either n squared or it's 2n squared. And this is the number of degrees of freedom you lose because you are metric preserving, right? And it's f is either 1 or 2. And then you lose, this is the off diagonal, right? This is the off diagonal. And then this is the diagonal degrees of freedom that you lose. And so you end up with this expression for real or complex. But for the quaternions, notice everything is the same. F is 4 like we would expect for quaternions. But all of a sudden, when it comes to the diagonals, f is 3. And I'm not actually sure why that is. He mentions it in the text of the book, and he shows it up in this equation, and he splits out the quaternions from the real and complex numbers here. But I'm not quite sure why that number is 3. I've kind of worked on it, and this is the first time I've noticed it in preparation for the lectures. When I've never noticed this before. But you lose a constraint there. And I'm not quite sure why. So, challenge to anybody out there, if you can dig into this and figure out why. I'm sure it's pretty simple. I'm sure this is not a complex thing. I'm just missing it. But notice in the unitary case, right, he doesn't split out the quaternions. So here f is 1, 2, and 4 straight up. But notice n doesn't have an f in front of it because of the unitariness drives those diagonal elements to be real, which means they're effectively only one constraint equation. Okay, so that is basically how this counting process is done. There's another great chart to sort of sum up where we are with all of this, right? The general linear group and this is for complex. This is just for the complex case, right? I've just looked at the charts. That's the most common one you wanted to know anyway. But the general linear group starts with 2n squared degrees of freedom. And if it's metric preserving, you are forced into, these are the metric preserving versions of the general linear group. And this is the symplectic metric preservation, and it ends up being n times n plus 1 degrees of freedom ultimately. The orthogonal is n times n minus 1 degrees of freedom, and unitary is just n squared degrees of freedom. Then once you're metric preserving, you may or may not be volume preserving. Now, when we talked about volume preserving, we talked about the SLNC, so that's this line here. It turns out there's two subgroups that are also volume preserving in a slightly different way, and we're not going to get distracted by them, but it has to do with the fact that the modulus of the determinant could be 1 in two different ways. But ultimately, the special linear group, the number of degrees of freedom there is 2 n squared minus 1, right, where we lose that because we're forcing the diagonal to be 1. So it's really 2n squared minus 2, right? It's really 2n squared, let me get the drawing here, minus 2, because you're forcing the real and the imaginary parts both to separately be 1 and 0. And so this guy's volume preserving, but it's not metric preserving, which is why the arrow goes right through it. But then you have the volume preserving groups that are metric preserving, and that's the special unitary group of the complex numbers, the special symplectic groups. Either I show you it's SSP, right? That's the special symplectic group and the special orthogonal group. And then the intersection of this special unitary group and the special symplectic group gives you the unitary symplectic group. And these, of course, are, this is sesquilinear metrics here, and this is bilinear metrics here. And interestingly enough, this guy lives sort of in the world where it'll preserve a bilinear or a sesquilinear metric. So there's a chart like this for each of the reals, complex, and quaternions in Gilmore.
And before we go, I want to look at this last chart in Gilmore at the very end of his chapter on classical groups, where he has this interesting list of classical groups on the left and on the right. And what he's trying to say is the fascinating and sometimes well-known fact that there's isomorphisms between these groups, meaning effectively these groups are not necessarily different. The most famous one is right here, right? SU2C and SOR, meaning SO3R, right? The special orthogonal group in 3 dimensions with the real, it's orthogonal reals, special orthogonal group over the reals, and the special unitary group in 2 dimensions over the complex. Those are isomorphic. And it's also well known that it's isomorphic to the unitary group over the quaternions. If you know much about computer science, right, you'll discover that a lot of rotations in computer science are done using the quaternionic math. And so this, of course, you learn about this when you learn in physics about Euler angles, and then you learn about this in quantum mechanics, and you make the connection in quantum mechanics. This connection you don't make unless you're like programming computer games or something. But what's interesting about this is there's all these, we now know how to read this chart, right? We've understand all of these groups, except actually we didn't do SO star 4 and SU star 4 or SO star 6 or any of the SO stars. That has to do with the quaternions and understanding the quaternions in terms of complex numbers or real numbers. We won't get into that. It's fascinating, but a bit of distraction, and it's a little esoteric too. But most of these isomorphisms are not at all obvious, right? Like SO4R is SU2C direct product with itself, right? You'd have to, you have to work to figure all that out. And this is just a chart showing some examples. What's important, though, is this thing on the left side of the chart, this dimension. So now understand, where the word dimension starts to kind of get out of control, because we know that SU2 over the complex numbers, it's working on a vector space of dimensionality 2, right? So this is going to represent basis changes of a two-dimensional complex vector space with a sesquilinear metric. And this, for example, is a three-dimensional real vector space with a Euclidean metric. So the dimensionality, there's a dimensionality of these underlying vector spaces whose bases are transformed by these group elements. We're going to get into that a lot in the next couple lessons. But the dimension of this is listed as 3. And so this dimensionality is the number of degrees of freedom that it takes to specify these matrices. Now notice the unitary quaternions, you'd think, okay, well, quaternions have 4, it's in one dimension, but unitarity forces the modulus to be 1, so you lose 1 degree of freedom. So that may have something to do, by the way, with this whole question. I'm sure it does. I'm just not seeing it. But the number of degrees of freedom to construct these matrices is different than the dimensionality of the underlying vector space whose basis is being transformed, and it's certainly different than the number of separate matrix elements. So the matrix elements are tied together by 3 different degrees of freedom here, 3 parameters, and that's going to be a huge deal coming up, because ultimately we're going to turn this into a topological space that's a manifold of 3 dimensions. So it's going to be a 3-dimensional manifold is going to build this group. Likewise, these guys have 6, 10, 15. These numbers here are basically the solutions of these expressions here, right? These expressions on this page, you put in this calculation and you will get, you'll basically be getting these numbers here. Now, these are all the special groups, so it's not exactly these. You also have to, these here are not the special groups, in other words. But equations like this that apply for the special groups, well, I guess you could look at it here, right? So SU2C, n squared minus 1, all right? So we go back here. 3, of course, is 2 squared minus 1, right? So that's where these numbers come from. So anyway, we'll start getting into the significance of these numbers and how to start thinking of these groups as topological spaces in our upcoming lections. All right, bye-bye.